Yes, so obviously I am sick today. Sick all day yesterday too, but I don't want us to fall behind. So I'm going to explain the stuff that we were going to learn today and then make another video for the worksheet that you guys have to do. Okay, so let me share my screen. Okay, so these are the notes that you need on that peach paper. The sub should have passed it out. And you can just copy them. I'm going to explain 5.1 first. So this is concentration versus time. If you took my class last year, you learned this. We played dodgeball to kind of demonstrate how, the reactants start with all of the dodgeballs. And then the products don't start with any, and then they start to go towards the products, and then dodgeballs are going back and forth and back and forth. Okay. So this graph, the axes are labeled concentration, which you should know that the brackets right here, that represents concentration. So a lot of times in this unit, you won't see molarity written. It'll just have these like square brackets or molarity. And then this is time. Can be in seconds, hours, years, like reactions take different amounts of time. And so it really just depends on the reaction. Okay. So we can see that this line is going down. So that means it's the reactants, right? Because we start with something. So when you have a reactant, you start with it. And it just happens to be labeled B. I don't know. It can be anything, right? It's just a letter. Obviously, it's a chemical, but we're just using variables to represent it at this point. And I put a little down arrow just to remind you that the reactants are always the ones that are going down because that's what you start with and they start to get used up. And then the products, well, you don't start with those, right? Because they're the products. That's what you end with. And so you don't start with anything. It's down here at 0. And then as the reaction proceeds, we get more and more concentration until these lines are kind of straight. And that's when it's at equilibrium. We'll learn more about equilibrium in Unit 7. But for now, we're just sticking with this. Okay. So if you were to, well, actually, I can just skip this right here. I'm going to go down here and then we'll come back to this. If you were to calculate the rate of disappearance of B, so this is just rise over run, right? So you can see that B changes 2. Okay, so it goes from 10 to 8. This is the absolute value, so it doesn't matter, right? So it's 2 molarity per how many seconds? 5 seconds. So that's how long it took to decrease. So 2 divided by 5, you could do that as a decimal, and the units of that are molarity per second for this problem. Okay, for this one. And then the rate of appearance for A, you can see A comes up a little bit faster, right? So you can see within the same 5 seconds, it actually goes up 4 molar, right? So the concentration increases by 4. So that's going to be 4 over 5 seconds. So what you can see is A increases at double the rate that B decreases at. And so what that means is we're going to put a coefficient 2 in front of A because we get twice as much of it in the product as we used up in the reactant for B. Okay, so this would be my balanced equation. Prepared to see lots of these types of graphs with different ratios of reactants and products. Okay, that's 5.1. 5.2, a really long section. This is just one part of it. This is reaction orders from experimental data. So I should have started with, we are learning about kinetics. That's the unit that we're on. We're skipping 4. We're going to go back to it later. But Unit 5 is all about kinetics. And really that's just how fast reactions happen, how you can speed up or slow down reactions. I really like this unit. It's very unique. Anyway. A reaction order is a way to tell how fast a reaction is happening and at what pace it's proceeding at. Okay, so some reactions start really slow and then they go whoosh and then they like start to increase quite a bit. Some just are a linear progression. Some just stay at the exact same rate the entire time. So it really depends. And those orders, how fast those different types of reactions happen or how they change over time, really, it's not how fast, are given numbers, right? So there's 3 different types. There's 0 order reactions, 1st order reactions, and 2nd order reactions, okay? We hear a lot about this. There's many ways to figure out the order of a reaction. One of the ways is to look at experimental data, okay? And that's what we're going to be doing right now. There's other ways to figure it out that we'll learn about in other sections, okay? But that's a big focus of this unit is just figuring out the order of reactions, okay? So here we have three different trials or experiments, sometimes they're called. We have the concentration of A and the concentration of B. I use these same variables. They don't have any correlation to the data that I second or hour, whatever the units of time is. Okay. So anyway, what you do to figure out the order is you compare this experimental data. Okay, so you can see that in trial 1, concentration of A was 2. Now in trial 3, the concentration was 4, so it doubled. So from 1 to 3, it doubled. And if you look at the rate for trial 1 to 3, it goes from 1 to 2, which is also doubling. And if you look at the little key right here, if you double the concentration and then the rate also doubles, then that would be first order. Now, it doesn't have to be doubling, it could be tripling and then tripling. It's really just doing the same thing, okay? It's first order. So that's how we know A is a first order reactant. Okay, so what that means is that it's going to be, we'll get more into it later, but really just like the reactants are going to be decreasing at kind of a, it's going to be an exponential curve. Okay. And then B, what we're going to do is we're going to look at trial 1 and trial 2. So you can see it goes from 3 to 6. So that is doubling. And then if we look at the rate in trial 1 to 2, it goes from 1 to 4. So it quadruples this time. So we can see that the B concentration of B doubles and then the rate quadruples. And my little key right here, times 2 times 4. Now it doesn't need to be times 2 times 4. It's just to the exponent, right? So if it was times 3, it'd be times 9, right? But usually this is what they use. Okay, so that means that B is second order. Okay, so that's the rate is going to be a little bit different in how it progresses. So the rate law, what you do is you do rate equals K. We'll talk a lot more about K later, but it's just a constant for now. And then you take the concentration of A, and then we said it's first order, so you raise it to the power of 1. And then we said B is second order, so you raise it to the power of 2. Now, if it was 0 order, you'd raise it to the power of 0, which would then just turn it into 1, which so then you wouldn't have to write it. But this is something called the rate law. We'll be looking at this quite a bit. Only thing that you might be confused on is why did we skip 2 when we were going from 2 to 4? Well, the reason is you need the data in the other column to be consistent, right? So I went from 1 to 3 as opposed to 2 to 3 because I can see the concentration of B was 3 and plus, saying bless you to my dog. Anyway, so it goes from 3 to 3 right here. So it's staying consistent. So that's how I know to go from 1 to 3 and not 2 to 3 for concentration of A. Same thing for B, right? I want to go from 3 to 6, not 3 to 6 right here because it's consistent in A. You don't want to change too many variables. Okay. And that's what this information is all about. I know it's kind of complicated while I'm not there, but hopefully that was helpful.